So just like what we did in lecture 4, so recall ridge regression and lasso, we've got to do regularization for neural networks, right? So we need to somehow prevent neural networks from overfitting. Right? So let's first look at some popular loss functions for artificial neural networks. We have seen this binary cross entropy, multi-class cross entropy, mean squared error for regression, mean absolute error for regression. So these are loss functions. So how do we do regularization? So just in the same way as we did when we introduced the ridge regression and lasso, we can modify this loss function by adding a regularization term, right? So if we add the sum of squares of all the weights of our neural network, this is L2 regularization. If we add the sum of absolute values, this is going to be L1 regularization, right? So in both cases, the coefficient lambda is called the weight decay. Right? So here is, so this is our original loss function. So this is the mean squared error. This is original loss. And then this is the regularization. Now, same thing for categorical cross entropy. So this is our cross entropy. And this is the term that does regularization. So this is the regularization term. So basically, the regularization term prevents the model from being too complex, right? So it penalizes it for being too complex, and the too complex means that it has too many large weights, but not biases. Biases are somehow okay, but weights, having too many large weights is not okay. And a completely different type of regularization for artificial neural networks is something that does not have analogy for other types of models. So it's just for networks. Is called neuron dropout. So the idea is that in the training phase, we are going to ignore a random fraction of nodes and corresponding activation functions, right? So they're going to be dead. So when we are training our neural network, so these neurons are going to be dead. But in the testing phase, we are going to use all the activations, but we are going to reduce them by the factor of p to account for the missing neurons. Now, the idea is, again, so this operation, since we are randomly removing some neurons, these operations are going to prevent the final output to be too much dependent on a particular neuron, because this neuron is going to be out. I mean, sometimes it's going to be switched off during the training phase, right? So for some training examples, it's going to be on. For some training examples, it's going to be off. But overall, it prevents the final output to be too dependent on a particular neuron, right? And this is, at the same time, it prevents, it kind of penalizes the network for being too flexible and for trying to overfit the model. So this is also a type of regularization. And both weight decay lambda and the dropout rate, hypothetically, they can be tuned by cross-validation, but cross-validation only makes sense if we have little data, right? So if we have a few hundred training examples or a few thousand training examples, then yeah, sure, we can do this by cross-validation. But usually, artificial neural networks are used when we have just a lot of data, like millions of examples. And in that case, we don't really bother with cross-validation because it would be too time consuming. So in that case, the optimal choice of hyperparameter values is done by a grid search on some validation data. Okay, so this is the end of part 10, and please do the quiz.